Today we're on page 10 of the Chapter 14 AP Chemistry packet. We're going to be discussing the strength of acids. We're going to start with the hydrogen halide acids, which are the ones with the group 7, and then we're going to go to the oxyacids, the ones that contain oxygen. Starting with the hydrogen halides, we're going to go down group 7, fluorine, chlorine, bromine, iodine, and let's take a look at all these acids. We know that the three strong ones out of here are Hickel, Hibber, and High. These are our three strong acids. HF is not a strong acid. So you may be wondering, why is HF not strong while all these are strong? We're going to look at two factors, bond strength and bond polarity. If you want to have a strong acid, okay, that means that you have to be able to give up the H. So if we take a quick look at the Lewis structures, you know that an acid with a halide is going to be HX. The reason is this has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. This has 1, so when they share, you've got a covalent bond. Okay? The strength of this bond will contribute to whether this is a strong or weak acid. If it's a strong acid, what you want is you want this bond to break easily. If the bond breaks easily, that means it must be a weak bond. So to have a strong acid, you need to have a weak bond to be a strong acid. Okay, also we're going to look at polarity. Polarity is where the H and the halide, the X, do not share equally. All right, so you know that the halogens have high electronegativity, so it's going to be delta negative on that side. This is going to be a delta positive. You could also use that little arrow. This is not the coordinate bond. This is just the polarity bond arrow to show the polarity of the bond. Either way, you know you're going to have the electrons going towards the halogen. So the more the halogen pulls these electrons, the more easily this H can be given away. So you want to have a high polarity in this. Okay, you want to have a high bond polarity. High bond polarity is what you want. Okay, so the polarity of the bond is going to be a factor, and the bond strength is going to be a factor. Okay, and that's going to contribute to whether or not this is a strong or weak acid. So strong acids want to have a weak bond and a high bond polarity. That's what they want to have. So now let's take a look at the acids in our list. They are going to follow a trend in both strength and polarity. So the strength of HF bond, this strength of the bond, is a very strong bond between these two. And then as you go down the list, they get weaker and weaker and weaker. All right, this will have to do with the size of the F, because this is the smallest atomic radius, and then they get bigger and bigger and bigger. So the smaller the radius, the stronger the bond here. So there's going to be the strongest bond. Also, F is the most electronegative element on the periodic table, so the bond polarity will also be the most for HF. So although it has a good polarity to make it a strong acid, the strength is too strong of the bond, is too strong, so it cannot break easily. So therefore, HF is not a strong acid. Now HCl, the bond strength decreases while still being fairly polar, and that combo contributes to HCl being a strong acid. And then the BR-H bond is even weaker and not as much polarity, but because it is a weak enough bond, this can break as well, and the same thing with the iodide. So if you ever had a question where you had to compare these and decide why is HF not a strong acid while all these are, the answer is that the bond in HF is too strong, cannot be easily broken, and so the H is not easily ionized. However, the ClBr and I, the bond strengths are weak enough, coupled with their high bond polarity, making the H's easily ionized. Now we're going to take a look at oxyacids. Oxyacids are acids that contain oxygen. The consideration here is twofold as well. You're going to look at the number of, well, all right, we'll do the electronegativity of the central atom and the number of oxygen atoms surrounding it. So we'll start with electronegativity. you want to have a high electronegativity of the central atom, and you want to have lots of oxygens. So let's actually start with the oxygens. Look at how many oxygens are in HNO3. We have 3 of them, okay? However, we only have 2 in HNO2. We have HCl4 has 4, and the rest of them have 3, 2, and 1. H2SO4 has 4, and the rest of them have 3. the other one. Okay, H3PO4 has 4, and H3PO3 has less, and H2CO3 also has that. So the strongest acid out of every set is the one with the most O's. So this is the most O's is the strongest out of these 2. This is out of these 4. This is out of these 2. This is out of these 2. And that's just on its own. Now the question is, well, why are these 3 strong and these 2 are weak? So what we need to do is we need to look at the electronegativity of the central atom. So if you look at a periodic table on the right side, you're going to see that N, O, and F are in the first, well, really the second period, and then P, S, and Cl are in the third period. You know that F is the strongest electronegative element, okay? So any acid with a central atom that is close to F is going to be a stronger acid. So notice that Cl is very close to F, and HClO4 is a strong acid. Notice that HNO3 is strong, and N is fairly close to F in electronegativity. Notice that H2SO4 is strong, and S is fairly close to F in electronegativity. However, look at H3PO4. See that? That one is not as close to F in electronegativity, and so that one is not going to be a strong acid. And carbon is over here. Notice that one is also not as strong of electronegativity. So, to understand this one more time, there are 2 factors. It's this electronegativity and the number of O's. So electronegativity for N, Cl, and S are high because they're closer to fluorine on the periodic table, which if you had to really explain it's because their size is smaller. However, C and P are not as strong, and so these acids with those central atoms are not strong acids. They're weak acids. All right, let me give you one more thing to help you understand about the number of O's and why that works here. If we look at Lewis structures, so let's take HNO3. We'll draw nitrate first. So here's nitrate. It has 5 valence electrons. I'm going to draw it like this because I know what's coming next in my little explanation here. I'm going to draw 1 O right over here, 1 O right over here, 1 O right over here. Give myself a little extra room. And let's draw 6 electrons for each of these O's because they're in group 6. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Now, of course, we also have an H because it's HNO3. I'm going to save that for when I'm ready. Okay, so let's take a look at the bonding. We can bond this O over here. We could bond this O over here. We could also double bond on the right. And then remember the trick to get this left O, we would move this electron over and then do what we call the coordinate covalent bond right here. And then you could see that the H can easily attach right here with its electron. Okay, so of course we're going to draw a final copy for this a lot neater. So here's our N in the middle, O on the right, O on the bottom, O on the left, and the H is going to be right over here. So bonding, this is going to be the coordinate, which you could just do as a regular line. This is a double bond. This is a single bond. We have 3 pairs on the O on the left. We have 2 pairs on the O on the right. We have 2 pairs on the O on the bottom. And then we have that single bond with the H. And that's all we're going to have for this Lewis structure. So what's going to happen is, with electrons, you know that O is very electronegative. So the more O's you have, okay, they're all grabbing these electrons in the bonds. They're actually taking the electrons from this bond a little more as well. So because these electrons right here in the H to O bond, don't call this a hydrogen bond, by the way, because those are intermolecular. This is intra. But the bond between the hydrogen and the oxygen, the electrons are drawn away towards the middle, and that, again, is contributed the electronegativity of this central atom contributes to that, as well as the number of O's contribute to that. So the the whole process is drawing the electrons away. So this H right here can easily just be lost as an H+, and then this stays together, nitrate, as an NO3-. So you've got your H plus right here, and then you've got your NO3- right here, and that's what makes this a strong acid. Okay, so the two factors, lastly, is electronegativity of the center, which happens with N, S, and Cl, and the number of O's as well, because they're high in electronegativity, are going to draw the electrons away, and when that happens, this bond becomes weakened, and this goes off by itself, and this stays. And that's what's going to happen with HNO3, HICL-O4, and H2SO4, but not with phosphoric acid or carbonic acid.